This is Jack Jackson. This is a basic measurement concepts and the concept of dimension and measurement a little bit. So this is going to be an informal approach to this idea. So if we start with a point, we want to think of a point as just a location only. So it has no size or shape or anything to it. It doesn't even take up any space at all. So right away when we look at geometry and we're representing a point by a dot, then we're automatically misrepresenting things, really, because the dot takes up some space. But of course, if we just only had a point there, we couldn't see it, so that would be no good for representation purposes. So there's really nothing to measure with a point other than maybe its location in a plane, and so it takes up no size, no space. We call that 0 dimensions. Now, if we take a point and we move it in a certain distance a particular way, whatever we call 1 unit, that produces a unit segment, say 1 centimeter long, or 1 meter, or 1 yard or foot, or whatever, some unit length. And so that's a 1 unit length. Okay, now we're moving in one direction. We call that a one-dimensional object. Now, we can take a curve like this, and we can measure, like a straight line segment, we can measure that by placing those 1 centimeter segments end on end and count how many will fit there. So there are 4 of them there. Of course, this is dynamically works, so we can make 5 now, and so forth. And we can see how the length of that can change by adding or subtracting more line segments to our length. And so when we're measuring length, we're saying how many of the line segments can we line up end to end along the path. Now, it is possible for us to also talk about those lengths as on a curved path by bending this line segment without changing its length. But the basic idea is there, we line these up 1 centimeter at a time. Of course, what we're assuming here is that there is some sort of consistent scale that 1 centimeter over here is the same as 1 centimeter here. We can use the same one and just move it around. So that's the basic concept of linear length measurement, and so that's a one-dimensional object. So a whole line, for example, is infinite in length, but it's called a one-dimensional object. You can basically only go in one direction, and of course it's opposite, and so that's still called one-dimensional. So, for example, you could only go east and west, for example. Now, if we take a line segment now, here's our 1 centimeter segment, and we're going to move that 1 centimeter segment in a way that is at right angles to the to itself, so in a perpendicular way. And when we animate that, what do we get? We're going to end up with a unit square. And so we generate a square area. And so that area is going to represent a two-dimensional object. So now it's not only just the square, but the interior of the square really is more what we're looking at here. And so we have this little square tile, a unit square tile. So now notice we're going to move around along the line, we only move east or west, one dimension. If we're going to move on the square, we can move east or west and north or south. And so what if we want to find an area of something like this? Then the idea is, whereas over here it was placing unit lengths end to end, here it's placing unit tiles. And we take these tiles and we tile the area. And so area then is found by counting how many of these little tiles will fit on this region, in this region. And of course, very simple way of seeing that is just counting here, but of course counting, we can think of these as groups. So here we have 3 rows and 5 columns. Okay, so each row can be thought of as a group. So we have 3 groups of 5. So it's really the same as addition, adding 5, and adding 5. But repeatedly adding the same thing is another thing known as multiplication. So that's really what multiplication is. And so you can see this. So if we change this 3 rows and 4 columns, we get a total of 12. And what we're adding is these little square centimeters. So the unit is a square of a linear unit. And it's called, this is also why second power is called squaring, because in fact the shape that you get is actually a square. And so we're finding out how many square tiles. Now, if we want to do a three-dimensional thing, what we want to do is now take our unit tile, our little square tile, and we want to move that in a way perpendicular to this. Now, if we did this, actually it would come straight out of the screen towards you, perpendicular. We're going to simulate that, or straight away from you. We're going to have it simulate that by going away from you. Now, what we're assuming here is that these are all right angles here, and so what we get is what we call a cube. It has, so let's see what we have. A line segment has 2 endpoints, and then the line segment itself. A square tile has 4 vertices and 4 edges, and then the interior region. The cube, this is not going to be just a cube, but the interior of the cube as well, so we're going to think of this as a solid cube. And notice it has, count them, 8 vertices, 6 faces, which are these square tile interiors of the squares, and then edges. Let's see how many of those it has. Well, let's count them. There's 4 on the front, 4 on the back. That's 8, and then you got 4 coming out the sides. That's 12. So we got 12 of the edges there. Now, this gives us the ability to move in 3 dimensions. So it's not only north, south, and east-west, but also up and down. And if we want to find the volume of some solid region, then we're just stacking up these unit cubes here, and we're seeing how many of these will stack up here. And so we're stacking them up here and then lining them up as they go back and so forth. And so we can see where these things how these things stack up, and we can count them. So, of course, if you think about the area of the base here as just being like a rectangle here, okay, so for example, this one has let's see, the depth is 3, the rows are, these numbers don't seem to be matching out, let's see. The 6 seems to be right. Yeah, 4, that's right. The height is 4. Okay, so that's good. This is working. So let's say we make the height, well, the height could be 3, for example. So there we go. And then, so looking at the front face here, that's rows of 3. And columns, right now I have 6, I can make 5 there, whatever. Okay, 2, whatever, let's make 5. Okay, and so then we have an area of that front face of 3 times 5, or 15, and that gives you sort of your first layer here, but then we stack that back this way at a depth of 3, and so we end up with basically length times width times height here for the area of this rectangular kind of a solid. Okay, we'll define all these things a little bit later. Okay, so that gives you the idea of dimension. Now, in theory, at least, we can extend on into higher dimensions, 4th dimension, 5th dimension, and extend this. We'd have to extend a cube in a way perpendicular to all of the sides into the 4th dimension. And a little harder to visualize that. We're already stretching it a bit to try to visualize a 3-dimensional object in a 2-dimensional environment here. And then when we try to visualize a 4th dimensional object, it gets a little bit more difficult. But that's kind of one of the main ideas of the novel Flatland, is that it gives you some idea of looking at this.